In this video, I'm going to solve a problem on mechanical rotational system. Here is the question. Write the differential equations governing the mechanical rotation system shown in figure. Obtain the transfer function of the system. So we have the diagram which is represents the mechanical rotational system. So this is the diagram, and we can observe that it has the two mass elements which will provide the moment of inertia J1 and J2, and we have the two elements. So one is a spring rotation torsional spring K element, and friction element B. So by using this mechanical rotational system, we have to be find the transfer function. So that is given by Laplace transform of output divided by Laplace transform of input. We'll see that how we can find the transfer function step by step. So first we need to be identify that applied torque, that is denoted by T, is the input, and angular displacement theta is the output. Let's see that Laplace transform of T is given by T of S. Laplace transform of theta is given by theta of S. Laplace transform of theta 1 is given by theta 1 of S. Now, the final intention we have to be find the transfer function is theta of S by T of S, which is given from the definition of transfer function. That is the ratio of Laplace transform of output divided by Laplace transform of input. So here theta of S as in output and T of S as input. So this ratio we can call it as transfer function. The system has two nodes and they are masses with moment of inertia J1 and J2. The differential equation governing the system are given by torque balance equation at these nodes J1 and J2. So here the balance equation we can obtain that based on that sum of applied torques is equals to sum of opposing torques, which is given by the Newton's second law. We'll see this transformation we can obtain by solving that two differential equations that differential with respect to the J1 J2. So see that one by one. So first case one, the free body diagram of mass with moment of inertia J1 is shown in figure. The opposing torques acting on J1 are Tj1 and J2. So this is the two opposing forces acting on J1. Now these two can be represent the torque balanced equation. Tj1 is equals to J1 into d square theta 1 by dt square. Tk is equals to k into theta 1 minus theta. So these two are creating that opposing torques on J1. Now by Newton's second law, we can get this equation. That is sum of applied torques is equals to sum of opposing torques. So this is the equation Tj1 plus Tk is equals to T. Now, if you substitute this torque balanced equation in this equation, we'll get that J1 d square theta 1 by dt square plus K into theta 1 minus theta equals to T. So represent it is equation number 1. Now, the equation 1 is shown in the domain of time. Now, we have to be convert this time domain to S domain by applying the Laplace transform. So, now on taking Laplace transform to the above equation with zero initial conditions, we have J1 is a constant, right? So, J1 we have the same. And Laplace transform of second order differential equation, if you convert that S domain, you will get S square. S square into theta 1 of S plus K into theta 1 of S minus theta of S equals to T of S. Now we have to separate that theta 1 of S terms one side and theta of S terms one side. So then we get theta 1 of S into J1 S square plus K minus K into theta of S equals to T of S. So this is equation number 2. Now we have to solve the differential equation for the mass frictional element, the mass element moment of inertia J2. So here is the free body diagram with moment of inertia J2. The opposing torques acting on J2 are marked as Tj2, Tb, Tk. So these three opposing torques acting on J2. If you represent these three opposing torques by the torque balanced equation, we have this one. So Tj1 we can represent by J2 into d square theta by dt square. Tb is equals to b into d theta by dt. Tk equals to k into theta minus theta. Now this three torque balanced equations substitute by substituting equation which is obtained by Newton's second law, that is given by sum of applied torques is equal to sum of opposing torques. So for J2 there is no applied torque, right? We have to keep zero. These are the three sum of opposing torques. If you substitute these three torque balanced equations in this equation, we have the equation J2 d square theta divided by dt square plus b into theta d theta by dt plus k into theta minus theta 1 equals to 0. So this is equation number 3. Now, on taking Laplace transform to the above equation, we'll get the equation in S domain. So J2 S square. So instead of second order differential equation, we will get S square theta of S plus, instead of first order differential equation, we get S, that is Bs theta of S plus K into theta of S equals to K theta 1 of S. So just we bring this K into theta 1 of S in front to the right side. Now, the three terms having the common term theta of s, take it as common. J2 s square plus bs plus k will get k into theta 1 of s. So from this equation, we have to be get the equation of theta 1 of s in terms of theta of s. Theta 1 of s equals to J2 s square plus bs plus k divided by k into theta of s. Now, represent as equation 4. So finally, we solve the two differential equations for the both elements J1 and J2. Now what we have to do, so by solving these two equations, we can obtain the transfer function. So we have to be substitute equation 4 in equation 2 we get. So let's see that what is equation 2. So this is the equation 2. Here instead of theta 1 of s, we have to substitute equation 4. So equation 4 represents the theta 1 of s equation. If you substitute here, then we'll get the final transfer function. So let me see. So this is the equation after substitution of equation 4 in equation 2. So here we are replacing the theta 1 of s by this term, that is theta of s into j2 s square plus bs plus k divided by k, and remain term as this. So j1 s square plus k minus k into theta of s equals to t of s. Here these two terms having the common element, common term theta of s. By taking the common, then we'll get the equation j1 s square plus k into j2 s square plus bs plus k divided by k minus k equals to theta of s. By simplifying this term, we'll get theta of s into j1 s square plus k into j2 s square plus b2s plus k minus k square divided by k is equals to t of s. So the required transfer function is theta of s by t of s we have here, and this term will comes to the right side, then we'll get k divided by j1 s square plus k into j2 s square plus b2s plus k minus k square. So this is the transfer function for the given mechanical rotation system, which is similar to the mechanical translation system, but only difference is there the momentum is in a linear motion, here in a rotational motion. So the representation it is similar. So the both the in terms of so there we can represent that mass element by m1. Here we can represent that mass element by j1 because it is providing that moment of inertia. There the displacement we can represent by x, so x or y based on the notation. Here we can represent in terms of theta, so their linear momentum, here angular momentum, so rotation, right? So that's why the only notations are different and representation different, but the procedure is same to obtain the transfer function. Thank you.